This is the pre-laboratory video for your reaction stoichiometry determining a limiting reactant laboratory. And for this laboratory, we're going to use a reaction many of you have seen, the reaction that makes Alka-Seltzer fizz. And the reactants that are in Alka-Seltzer are sodium bicarbonate, also called sodium hydrogen carbonate, that's the more formal name, and citric acid, which has this formula here. One thing to know about citric acid is that it has the H3 written in front here because those 3 hydrogens are acidic, whereas these other 5 hydrogens are not acidic. So this is what's called a triprotic acid, meaning that 3 of the hydrogens can react. The hydrogen carbonate ion can actually act as an acid or a base. It could act as a base, as an acid, and make CO3 2- ions by losing a hydrogen, or it can gain a hydrogen to make H2CO3, which is carbonic acid. In this particular case, because it's reacting with an acid, citric acid, it will react as a base and gain a hydrogen. And what happens is that carbonic acid, when it's in high enough concentration, is unstable and it makes H2O as a liquid and carbon dioxide is a gas. And that's why it's a gas-forming reaction, and those are those reactants there. So what we're going to be doing is we're going to be using this reaction to analyze and predict and then test, verify which of these 2 reactants is the limiting reactant when we use them in different amounts. And so let's go through the ideas here. From a procedure point of view, what you're going to be doing is you're going to be making very careful mass measurements. And the key to your mass measurements is the change in mass from the total reactants to the total products. And there'll be a change in mass, which we'll talk about in a little bit. It's that change from when you go from reactants to products. There'll be a change in mass, which at first seemingly violates the law of conservation of mass, but as we'll see, it does not. So you'll be doing very careful mass measurements, so make sure you use the milligram scale balances and use the same balance each time. Practice pipetting 10 milliliter samples before you actually do your reactions for real to make sure you're doing that correctly. And make sure each time you clean and dry your beaker, and before each trial, measure the mass of the beaker beforehand, before you do your reaction. Okay. So let's go over the idea of a limiting reactant or a limiting reagent. They mean the same thing. Let's say that we have the balanced equation has 4 aluminum atoms react with 3 O2 molecules to make 2 aluminum oxide molecules. And let's say we're reacting 50 grams of aluminum with 50 grams of oxygen. Which of those is going to run out? Which of those is going to limit how much of our product can be made? And to do this, the first step is to convert each of those to moles. So let's do that first. So 50.0 grams of aluminum times 1 mole of aluminum over 26.98 grams of aluminum gives the moles of aluminum, and that's 1.85 moles of aluminum. And we can do the same thing for oxygen, 50.0 grams of O2 times 1 mole of O2. Because of O2, as opposed to just oxygen atoms, it's 32.00 grams of O2. That'll be a smaller number of moles because the molar mass is greater, so it's 1.56 moles of O2. And the easiest way to determine which of these is the limiting reactant is to just calculate how much aluminum oxide you would make from each of these 2 different molar amounts of reactants, and whichever one's smaller tells you which one the limiting reactant is. So 1.85 moles of aluminum can make, if we look at our ratio of 4 aluminum atoms to 2 aluminum oxides, we can make 2 moles of aluminum oxide for 4 moles of aluminum, and that tells us we can make 1.42 and that means we can make 0.925 moles of aluminum oxide. If we do the same calculation using the amount of oxygen we have, notice here the oxygen has a ratio of 3 oxygens go to make 2 aluminum oxides. So it's 2 moles of aluminum oxide over 3 moles of oxygen, O2, that makes 1.04 moles of aluminum oxide. So because the aluminum, the 50 grams of aluminum, makes less aluminum oxide than the 50 grams of oxygen, the aluminum is the limiting reactant. It can make less product, so therefore it's the limiting reactant. Notice also, by the way, that our oxygen was present in smaller molar amount than our aluminum was, but yet it is not the limiting reactant because you only need 3 oxygens to make 2 moles of aluminum oxide, but you need 4 aluminums to make 2 moles of aluminum oxide. So you really have to do the calculation out all the way. So that's how you can predict before reaction whether one reactant or the other is going to be the limiting reactant. Determine how much of the product you can make from each of those independently, whichever is smallest, that's the limiting reactant. The theoretical yield for the reaction is going to equal the yield predicted from the limiting reactant. So you always use, in this particular case, you use this molar amount of aluminum oxide, and convert that to grams to determine your theoretical yield in grams. You would not use this because that's more than you can make. Always use the smaller amount, the amount that the limiting reactant can make, to determine your theoretical yield. So if we do that, what we see is that if we take our 0.925 moles of aluminum oxide, Al2O3, and multiply that by the molar mass of aluminum oxide, 101.96 grams per 1 mole of aluminum oxide. Get over there, line. That gives you 94.3 grams of aluminum oxide. And that's the theoretical yield. The other thing you can determine is how much excess reactant exists for if you have one reactant that's not used up. So what we want to do is we're going to find out how much of the reactant in excess remains. The aluminum was the limiting reactant, so we're going to have some oxygen left over, and we want to know how much. To do that, we make what's called an amounts table. And it's a table that shows the initial amount you have in moles, what the change is in moles, and what the final amount is in moles. And it's a good way of just keeping track of what happens in the reaction. So we put in our initial amount of moles for each of these. So it's 1.85 moles of aluminum, 1.56 moles of oxygen, and we start with no moles of aluminum oxide. And we know that the aluminum was the limiting reactant, so it all goes away. So minus 1.85 moles of aluminum, and we end up with no aluminum. The aluminum oxide, we know we made 0 plus 0.925 moles of that, and so we end up with 0.925 moles of aluminum oxide. But the key is what happens to the oxygen. And what we need to do is we need to find out the change in oxygen so we can determine how much oxygen is left over. To do that, we use the molar relationship in the balanced equation between aluminum and oxygen. And so we know that 1.85 moles of aluminum are reacting. So you take what you know, 1.85 moles of aluminum, put that on the left, and then figure out how many moles of oxygen that will react with. So it's 3 moles of O2 for every 4 moles of aluminum. And that'll tell you how many moles of O2 are reacting. And that comes out to 1.3875 moles of O2 reacting. And I'll just use the extra significant digits for now. So that is how much reacts, 1.3875 moles of that. And therefore the amount remaining is going to be the difference between that and 1.56. So it comes out to 0.1725. That's how many moles of O2 remaining. And then you can convert that into grams. So 0.1725 moles of O2 times 32.00 grams of O2 per 1 mole. And that gives you a mass of 5.52 grams of O2, and the way we say that is in excess. Okay, now let's move on. In your lab, what you're going to be doing is you're going to be calculating how much reacts. And so the first thing you need to do is you need to balance the equation. So let's just go through that now. This is a triprotic acid, so it reacts by giving up 3 H plus ions. Each of the bicarbonate ions, or sodium hydrogen carbonate, each mole of that compound will gain 1 hydrogen. So 3 of these will react. Each one of those that reacts makes 1 water and 1 CO2. So you make 3 waters and 3 CO2s. And you'll make 1 sodium citrate from your citric acid. The key measurement in this reaction, which we said at the beginning, is the delta mass, the change in the mass from beginning to end of the reaction. And the change in mass is actually the carbon dioxide, because everything else stays. It doesn't matter that they reacted. The only thing that matters is if something leaves. And so what happens is the CO2 has left. And because it's left, what that means is that that mass has gone away. So the change in mass is equal to the grams of CO2. And so in your calculations, you'll take grams of CO2 and convert that to moles of CO2. And the moles of CO2 is going to be appropriate for how much sodium hydrogen carbonate reacted, or how much citric acid reacted. And so what you'll be able to do is you'll be able to test which your limiting reactant was by comparing moles of CO2 that were lost, which you get from your mass measurement, to how much sodium hydrogen carbonate was available and how much citric acid was available. The one that matches was in fact the limiting reactant. Okay, finally, safety for this lab. The biggest issue with this, of course, is, as in many labs, is getting things in your eyes. And for the most part, things in this lab are not terribly toxic and not particularly corrosive, because they're used in Alka-Seltzer, but we're using different concentrations and you don't know how bad that will be. So there are acids and bases and you should treat them as such. And the biggest problem here is actually that things are bubbling and foaming, and as such can spit out and get things on your skin or in your eyes. So always wear eye goggles and always wash when you get anything on your skin whatsoever. And that's the end of this pre-lab.